Welcome to the deep dive. We're here to cut through the noise, get to those aha moments on complex topics. Today we're tackling something really fundamental, maybe even a bit mind-bending, that powers so much of modern AI. It's about how models like GPT, like BERT, seem to, well, understand language, images even, in ways that feel almost human. How does it know bank means riverbank, not money bank? Or figure out what it refers to, like 5 sentences back. There's this core thing making it work.
Yeah, we're talking about attention mechanisms. Seriously, this isn't just some add-on feature. It's kind of the secret sauce, wouldn't you say?
Absolutely. It's the engine behind the most powerful AI models we see everywhere now.
So our mission today is to unpack exactly how these mechanisms let AI make sense of complex stuff, sequences of information, enabling all these breakthroughs we see every day. We've gone through a stack of expert sources, and we're going to pull out the key insights, try to make this pretty complex topic feel, well, accessible for you. Okay, let's get into it. Right. And what's really amazing here is just how audacious the transformer model was back in 2017. It wasn't just an improvement, it fundamentally reshaped everything. It's the cornerstone for models like GPT and BERT. But, to really get why it was so huge, we kind of need to look at the problems it solved first.
Okay, so before transformers burst onto the scene, what were we dealing with? What were the main AI models for, say, language, and what were their big headaches?
Well, for sequential data like text, the main players were recurrent neural networks, RNNs. The big problem with RNNs was they processed information strictly sequentially, one token, then the next, then the next.
Like reading a book one word at a time, but maybe forgetting the beginning by the time you reach the end.
Exactly. Imagine a long sentence, and it refers back to something mentioned way, way earlier. RNNs really struggled with those long-range dependencies. They'd lose the context, and the step-by-step processing had a huge practical problem. You couldn't really parallelize the training effectively. It made them super slow and computationally expensive, especially for long sequences.
Right. And what about CNNs, convolutional neural networks? They were amazing for images, right? How did they do with text?
Yeah, CNNs are fantastic for local patterns, finding edges in pictures or maybe short phrases like n-grams in text, but they lacked that bigger picture view, that global contextual understanding. They couldn't easily connect distant parts of a sequence, plus older models often use these fixed word vectors. Bank always had the same numerical meaning. River or money didn't matter.
So no dynamic meaning based on content.
Precisely. They couldn't adjust on the fly based on the surrounding words, which is absolutely critical for understanding language properly.
Okay, so we had RNNs forgetting things and CNNs missing the big picture. What was the big idea, the breakthrough that let us handle these complex sequences better?
That breakthrough was self-attention. It was specifically designed to tackle those limitations head-on. Instead of one token at a time, self-attention looks at the entire sequence in parallel, all at once. And it directly figures out how any two words are related, no matter how far apart they are. This allows for what we call dynamic contextualization.
Okay, self-attention. Let's zoom in there. Intuitively, what's it doing? How does it look at everything simultaneously without, information overload?
Think of it like this. Each word, or token, gets to focus on all the other words in the sentence. It's a bit like being at a noisy party, right? You naturally tune in to the voices that matter to your conversation and kind of filter out the rest.
Or like a spotlight, and I saw that analogy.
That's a great one. A spotlight that dynamically highlights the most relevant words on the stage for understanding the current word you're looking at.
That makes sense. So if we have, like, the animal didn't cross the street because it was too tired, self-attention helps the model shine that spotlight from it back onto the animal, ignoring street or cross. It finally gets the attention it deserves.
Literally. And the mechanism that makes this possible, the elegant part, is the Query Key Value Framework, QKV. For every single token, the model learns to generate 3 distinct vectors: a query Q, a key K, and a value V.
Okay, QKV. I found the web search analogy really helpful here. Can you walk us through that?
Yeah, it maps really well. The query Q is like what the word is looking for. It's question, like your search term in Google. The key K is like an identifier or a label for each word. Think web page titles or keywords. It helps determine relevance. And the value V is the actual substance, the information content of that word, like the content on the web page you actually read.
And these aren't fixed. They're learned.
Exactly. They're derived from the input word embeddings, but multiplied by these special weight matrices, WQ, WK, WV, that the model learns and optimizes during training.
So every word has its Q, K, and V. How does the model then use those to compute that spotlight effect? What's the math doing to figure out how much attention word A pays to word B?
It's a process called scaled dot product attention, 4 main steps. First, you compute attention scores. You take the query vector of the word you're focusing on,
Yeah.
and you calculate the dot product with the key vector of every other word in the sequence, including itself.
And the dot product measures similarity,
Yeah,
right?
essentially, yeah. Similarity or relevance. A higher score means a stronger potential connection.
Then there's that scaling step. Dividing by the square root of something. Why is that important?
Ah, yes. Step 2, scaling. You divide those raw scores by the square root of the dimension of the key vectors. This isn't just random math. It's crucial. It helps prevent the gradients, the learning signals, from becoming too small, vanishing gradients, or too large during training. It keeps things stable, especially when you have lots of dimensions.
So it stops the numbers getting out of control and messing up the learning.
Pretty much. Without it, the dot products could get huge, push the next step, the SoftMax, into regions where it doesn't learn well.
Okay, scaled scores. What's next?
Step 3, SoftMax normalization. You apply the SoftMax function to those scaled scores. This transforms them into a nice probability distribution. These are your final attention weights. They're all positive and they all sum to 1. It clearly shows, as a percentage, how much focus or attention this word should pay to every other word.
A distribution of attention. I like that. And the final output, the word's new representation.
That's step 4, weighted aggregation. You multiply those attention weights, the probabilities, by the corresponding value v vectors of all the words. You then sum these weighted value vectors up. This creates a weighted combination, essentially blending the information from the relevant words, giving you the final contextualized representation for your original word.
And that's how it adjusts the meaning dynamically based on context.
Super powerful.
But, okay, a single run of this self-attention. It sounds like it might latch onto one main type of relationship. What about words like bank, with totally different meanings? Or different kinds of connections, like grammar versus meaning?
That is a key insight. And that's exactly why we have multi-head attention. You're right, a single attention mechanism, a single head, might get stuck on one interpretation or struggle with that kind of ambiguity, polysemy. Multi-head attention basically lets the model focus on multiple aspects simultaneously. It runs several attention calculations in parallel.
So it's not just running the same thing multiple times.
No, it's more clever than that. It splits the computation into, say, the dollar parallel heads, maybe 8 or 12. Each head gets its own set of learned Q, K, and V weight matrices. So each head learns to project the input into a different subspace, focusing on different things. They all compute their attention outputs independently. Then these outputs are simply concatenated, stuck together side by side.
And then combined somehow.
Right. There's a final linear transformation using another learned weight matrix, $2, that blends these diverse perspectives from all the heads into a single, unified, richer output vector.
Ah, so it's like having a panel of experts. Each looks at the sentence from a slightly different angle.
That's a fantastic analogy, an expert panel. One head might focus on syntax, subject-verb agreement, stuff like that. Another might focus on semantic similarity, what words mean. Maybe another looks for long-distance connections. Each head produces its own report, its attention output. Then you merge these reports for a much more comprehensive understanding than any single expert could manage.
Makes sense. So what are the concrete advantages of having all these experts working together?
Several big ones. First, diverse focus. As we said, each attention head can specialize. Research actually shows they learn to capture different kinds of relationships, syntax, semantics, local patterns, long-range stuff. This naturally leads to a richer representation. Blending these different views gives a more detailed and nuanced understanding.
And it helps with those tricky words like bank.
Absolutely. It directly addresses polysemy. Different heads can pick up on different contextual clues simultaneously to figure out if it's a riverbank or a money bank.
Sounds like it makes the model more robust, too.
Definitely. Enhanced robustness and generalization. It's less likely to be thrown off by noise because it has multiple perspectives. And importantly, for training these huge models, the parallel nature of the heads means improved learning efficiency, faster training.
Like having multiple processors working on the same problem.
Or multiple RAM modules, or even like different kernels in a CNN finding different features. Same principle.
Okay, so we have self-attention, multiple heads. But attention isn't the only thing in a transformer, right? How does it fit into the bigger picture and what else is needed?
Right. A really crucial piece we haven't dug into yet is positional information.
Ah, because attention itself doesn't care about word order.
Exactly. It's permutation equivariant. Dog bites man, and man bites dog. Attention sees the same collection of words. It needs to be told the order. Otherwise, well, you get nonsense.
Crucial difference there. So how do they add the order back in?
There are a few ways. The original paper used sinusoidal encodings, clever use of sine and cosine waves. Others use learned absolute positions, where the model learns a vector for position 1, position 2, etc. You also see relative position encodings, focusing on how far apart words are. And newer techniques like rotary position embedding or rope-E are becoming popular. These positional signals usually get added to the word embeddings right at the start.
Okay, so positional info is added. Now, thinking about the whole transformer, the encoder-decoder structure, where does attention show up?
It's used in a few key places. In the encoder part, which processes the input sequence, you have standard self-attention doing what we discussed, building those rich contextual representations.
Makes sense. What about the decoder, the part that generates output?
The decoder also uses self-attention, but it's special. Masked self-attention.
Masked. What does that mean?
It means when the decoder is generating word number 5, it's only allowed to attend to words 1 through 4 and itself. It's masked from seeing future words it hasn't generated yet.
So it can't cheat by looking ahead. Keeps it generating one word at a time based on what came before.
Exactly, maintains the autoregressive property. And then there's a vital link. Cross-attention between encoder and decoder.
Cross-attention.
Yeah, this allows the decoder, as it generates each output word, to look back and selectively focus on relevant parts of the input sequence that the encoder processed. Think machine translation, the decoder needs to attend to the right source words to produce the right target word.
Wow, okay. So attention is really woven throughout the whole architecture. It sounds incredibly powerful, but also expensive. Calculating attention between every pair of words seems like it would grow really fast with longer text.
You're spot on. That quadratic complexity, where n is the sequence length, is a major bottleneck. Double the length, quadruple the computation. Yeah, it limits how long sequences transformers can handle efficiently. But this is a huge area of research. People are developing clever efficiency improvements. Things like sparse attention, where each word only attends to a subset of other words, not all of them, or linear attention methods that approximate the calculation. Techniques like grouped query attention also help. The goal is to get the power of attention without the full quadratic cost.
So stepping back, what's the big takeaway here? What's the sort of intuitive power of attention that makes these models so capable?
I think it boils down to that dynamic routing or spotlight idea. For every single piece of information the model asks, what other pieces of information anywhere in the sequence are most relevant for understanding me right now? The attention weights provide the answer dynamically. This lets transformers just nail tasks involving long-range dependencies, handle contextual disambiguation, like our bank example, recognize complex structural patterns, and adapt its focus depending on the task.
It really feels like a fundamental building block now.
It absolutely is, and its inherent parallelizability was key to scaling up. It's become this foundational primitive, not just in NLP translation, summarization, chatbots, but now we see it revolutionizing computer vision with vision transformers, VITs, and also making waves in speech processing.
Yeah.
The real genius, I think, isn't just the math, which is elegant, but how this relatively simple mechanism can learn to pull out the most relevant signals from incredibly complex data, whatever that data might be.
What an amazing journey through attention. So just to recap, self-attention lets the model build context dynamically across sequences, and multi-head attention provides these diverse viewpoints for a richer, more robust understanding.
Precisely. And thinking bigger, the really profound thing about attention is its core ability to weigh relevance dynamically. It doesn't fundamentally care if it's text or images or sound waves. That versatility suggests it's going to be critical for future AI advances everywhere. You know, maybe future AI using even more advanced attention could spot connections in scientific data we've missed or anticipate needs, but attending to subtle cues. It truly feels like a primitive component of intelligence itself that we're just starting to understand and leverage. It's quite exciting to think about where it goes next.